Great. We can't contact Mr. Zhao, so we will continue the next presentation. This presentation is from Mr. Kai Yu. Mr. Kai is from the School of Mechanical Engineering of Shanghai Jiaotong University. His research interests include advanced vehicle transmission and control, vehicle system dynamics and control technology. His topic is MPC-based active engagement control and fault-tolerant control for electric disconnect differential. So welcome, Mr. Yu.
Honorable guests, ladies and gentlemen, good morning. I'm honored and proud to have this opportunity to speak at this meeting. Today, I would like to present my paper, MPC-Based Active Engagement Control and Fault-Tolerant Control for Electric Disconnect Differential. In this report, I will focus on the application of model predictive control and fault-tolerant control in electric disconnect differential, or we can call it EDD for short. Therefore, today's report is especially divided into 4 parts. In the first part, I will introduce the chassis configuration using EDD and the modeling process of transmission system, including EDD. The second part explains the engagement control logic of EDD in detail, as well as the design of active engagement controller and fault-tolerant controller. The third part carries out the simulation calculation of EDD bonding process under typical working conditions, mainly displays the simulation results and analyzes the reasons. The last part summarizes the full text and draws the main conclusions. Now let's move to the first part. The figure on the left is the chassis configuration of the front and rear independent drive hybrid vehicle containing EDD. In this configuration, the front axle is driven by engine and the rear axle is driven by motor, in which EDD is installed on the rear axle. When the clutch in the EDD is disconnected, the power transmission from the motor to the wheel is interrupted. At this time, the vehicle is in the front drive state and has good economy performance. When the clutch in EDD is engaged, the rear wheel gets power. At this time, the vehicle is in four-wheel drive state and has good power performance. ECU collects the wheel speed signal and sends the EDD engagement and disconnection command to the motor controller. The motor controller adjusts the speed and clears the torque of the motor before engagement according to the command of ECU. The vehicle can switch the driving mode according to the requirements of economy and power, and EDD is the key to realize the switching between two-wheel drive and four-wheel drive mode. The figure on the right is the structure schematic diagram of EDD. EDD has the basic characteristics of clutch, including planetary gear set, half-shaft gear set, differential bracket. The difference is that there is a dog clutch on the side of differential bracket. By evenly opening holes on the shell by driving end of the clutch is arranged outside the shell. In addition, the solenoid is also a key component. After being energized, the electric force is generated to push the driving end of the clutch to the right to realize the engagement of the clutch. And after the solenoid is energized, the clutch is disengaged under the action of the spring. In order to study the control strategy of EDD control engagement and disconnection, it is necessary to establish an accurate and practical dynamic model. The dynamic model should include the transmission system model from the motor to the wheel end and the clutch model that can respond to collision so as to fully reflect various working conditions of engagement, disconnection, and power transmission. The established dynamic model is shown in the figure. Transmission system models are generally established by mature methods. That is, torsion spring, damping, and launch initial are usually used to replace the shaft. Such a model is linear and simple. However, the dog clutch has strong nonlinearity, which leads to consider the collision between teeth and teeth. Even the collision of crown chamfer has to reflect the phenomenon of uneven engagement, such as tooth spitting caused by the collision of crown chamfer. In addition, even if the clutch is engaged, there is a tooth gap about 1.4 degree between the clutch teeth, which is converted to 14 degree at the model end, which means that idling may occur when the motor torque changes greatly, and there will be impact after idling, so this gap needs to be considered. The established of dog clutch model is the most critical and complex part of the dynamic model of the whole system. In this section, the contact force caused by mental collision is considered first. Then consider other external forces, and finally integrate them into a complete clutch model to reproduce the coupling motion of translation and rotation. The contact force of the clutch is relatively complex. This paper established the clutch collision dynamic model in 3 cases, in which the schematic diagram of case 1 to case 3 is shown in the figure. In case 1, the top of the clutch is uncleat because of the clutch is immersed in oil. The dynamic friction coefficient between metals is very small. Therefore, in the dynamic analysis, the influence of friction is ignored, and there is only axial force at this time. In case 2, the clutch chamfer gleeds. The displacement of the clutch is medium. At this time, there may be no collision, or the crown chamfer gleeds when the crown chamfer. The axial force and the tangential force needs to be discussed separately. In case 3, the clutch displacement is very large. At this time, there may be no collision or collision between teeth and teeth. After establishing the driveline model according to the above method, if the nonlinear driveline model is directly used for the model predictive control, the solving speed can hardly meet the real-time requirements. Therefore, the following reasonable realization of the nonlinear model is required. First, it is considered that the vehicle speed is almost constant in MPC prediction time domain. Secondly, rolling resistance can be regarded as interference. In a physical controller, the continuous state space equation cannot be directly used for calculation, so it is necessary to discretize the equation as follows. According to the current engagement condition, the engagement controller adaptively switches between active control and fault-tolerant control. The wheel speed is measured by anti-lock brake system sensor to eliminate the rotational speed of the passive side of dog clutch after vehicle control unit sends the engagement gesture. The next step is for the system to self-check whether there is a fault code. If no fault code is detected, it indicates that the active controller is trouble-free and the active control process can be applied. Otherwise, it indicates that the active controller fails and the passive control is applied. The specific process is shown in figure 4. Based on the model predictive control, the active controller aims to adjust the output Y to 0 before engagement. Thereby, the impact torque caused by teeth side collision can be reduced or even eliminated. To eliminate the change rate of torque of motor, the input should be expressed as an incremental form. To avoid the engagement failure, considering the malfunction of active controller or other components, an exhaustive fault-tolerant controller is designed. Thus, possible reasons of faults should be summarized before. Case 1 is the malfunction of active controller, and case 2 is the malfunction of displacement sensor makes it unreliable to judge whether the engagement is successful. Case 3 is the malfunction of motor makes the driving wheel lose power and become the driving wheel. And case 4 is the malfunction of solenoid makes the clutch unable to engage without the thrust. EDD, in order to issue the above faults, will not after driving safety. Fault diagnosis measures and countermeasures are designed respectively as shown in Table 1. The integrated controller combines an active engagement controller and a fault-tolerant controller. 3 typical scenarios are selected for simulation to verify the effectiveness of the integrated controller. The common initialization conditions are shown in Table 2, and the Simulink model is shown in Picture 5. Active control strategy is adopted when the components of EDD controller are intact and no fault code is detected in the system. The simulation results of active engagement control are shown in Figure 6. After receiving the engagement command at 1 second, the active controller immediately pre-accelerates the motor and then uses MPC to issue the rotational speed difference and the rotational angle difference converging to 0. The preparation of engagement is completed at 1.25 seconds and the engagement is successfully completed for the first attempt at 1.45 seconds after stabilizing for 0.2 seconds. In this process, the motor speed can quickly follow the wheel speed, and there is almost no overshot. Because of no teeth collision during the engagement, the clutch displacement quickly reaches 3.2 millimeter, which means the clutch is already in the engagement state. If a fault code is detected by integrated controller at the initialization period, the integrated controller will disable active controller and automatically change to the passive control mode. The simulation results of passive control, as shown in Figure 7, relies on teeth-to-teeth collision to eliminate the rotational speed difference. At 1.72 seconds, the rotational angle difference and rotational speed difference before the engagement are not eliminated. The clutch displacement at 0.8 millimeter appears stretching because of collision between the teeth top. Compared with the active controller, the total engagement time is extended by 0.15 seconds. When the active controller fails, the EDD control system detects the fault and switches to the passive control mode. The simulation results of fault-tolerant control as shown in Figure 8. The last part is the conclusion of this paper. The first one is to optimize the engagement process of EDD and reduce the impact touch of top clutch. An active controller based on MPC is designed, and the second is to augment the reliability of EDD and control system. Another fault-tolerant controller is designed, and the third is through the comparison of EDD simulation results. The effectiveness of active control algorithm in reducing clutch impact touch is verified. In addition, it is verified that the system can quickly switch to the fault-tolerant control mode when the active controller fails. Thank you very much for your kind attention.
Hello, Mr. Yu. Are you still online?